Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 4 of a unit current electricity. So let's begin with today's class. In today's class, first we are going to discuss about the classification of the materials. We know that materials can be classified according to their resistivity or conductivity, and based on resistivity or conductivity we can classify any material in three categories. They are the conductors, insulators and semiconductors. I hope you know that if I divide them or if I categorize them in according to their resistivity and conductivity. So if I talk about the conductors, semiconductors and insulators, then conductors having least resistivity, lowest. Conductors, according to the conductivity, they have a highest conductivity within this three. Second, semiconductors, their resistivity or resisting capability is moderate. Their conductivity, even it is moderate. For insulators, resistivity is the highest and conductivity is least. Even you have studied probably this in chemistry as well, conductors, semiconductors and insulators. So this is how we can segregate them. This is how we can segregate them according to their resistivity and conductivity. Let's see each of them one by one very quickly. Let's have a look. That conductors, we say that materials whose resistivity is negligibly small are called as the conductors. Examples: silver, copper, aluminum, all this are said to be a conductors. For your reference purpose only, I have mentioned the material and their resistivity at 0 degree Celsius. If you observe this very carefully, this is the table which which is not to be remembered. Yes, this is for your reference purpose only. Yes, if you can observe this very carefully, you will find that resistivity of this materials is very less, and as their resistivity is less, their conductivity is very high. I hope these things are clear. Is it clear? Let's move to the next material. It is an insulators. The second materials are the insulators. What we say about the insulators, they are the materials whose resistivity is very high, and that's why they are called as an insulators. So these are, for your reference, some of the materials that can be classified as an insulators, and their resistivity has been shown. Look at this. Their resistivity is in the range of 10 to the power 8 to the 10 to the power 11, and the highest resistivity is of rubber, that is, it is in the range of 10 to the power 16. If you compare this with the conductors that we have seen in the previous slide, they have a resistivity in 10 to the power minus of 8. I hope you understand the variation between these two. While insulator having a resistivity in the range of 10 to the power 16, or 10 to if you observe even the least resistivity, it is a 10 to the power 8 of wood. Then even then there is a big difference between the resistivity of these two materials, and that's why they behave completely differently. While conductors would be there, they will conduct very nicely, while insulators would be there, they are not at all conducting. Now let's look at the semiconductors. What we said about the semiconductors is that those materials whose resistivity lies between that of conductors and insulators, these materials are known as the semiconductors. Silicon is there, germanium is there, etc. Yes, this all materials can be classified as a semiconductors. We are going to learn this. We are going to learn the semiconductor in detail in a unit. The name, it's a semiconductor electronics. very important topic as per the NEET or JEE examinations. So we are going to learn this in more detail at that time. Yes, but if you observe the resistivity, their resistivity lies in the range of for carbon it is in the range of 10 to the power 5. For silicon it's a 10 to the power 2, and germanium it's in 0.46 only. So this materials have a resistivity which is on a moderate level between conductors and insulators. I hope those things are clear. Is it clear? Yes, great. Now let's look at the temperature dependence on a resistance. So to know the temperature dependence, first I need to define one very important topic or one very important term, that is the temperature coefficient of resistance, which we denote as an alpha. So let's begin with this. Consider a metallic conductor resistance which is having a resistance of R0 at 0 degree Celsius, and it is having a resistance of RT at T degree Celsius. So if I find out the change in the resistance, or if I find out the increase in the resistance, that RT minus R0 is found to be. Now one more reason is why resistance has been changed, because temperature has been changed. Look at this, it is T degree Celsius and initially it was a 0 degree Celsius. So what I know, that resistance is directly proportional to the initial resistance of R0 at 0 degree Celsius. I am talking about the alpha, and it is also the directly proportional to the rise in the temperature T. So it is something like this, that RT minus R0 is directly proportional to the R0. Even RT minus R0 is directly proportional to the T. So if I write this, let's say this is the relation number 1, this is the relation number 2, and if I write this in a single relation, it's an RT minus R0 is equals directly proportional to the R0 T. And if I remove this proportionality constant with a symbol alpha, then I can have RT minus R0 is equals to alpha into R0 into T, where alpha is the coefficient of resistance. I hope those things are clear. Yes, one more thing, alpha could be written as RT, that is resistance at T degree Celsius, minus R0, which is resistance at 0 degree Celsius, divided by R0. Yes, if you have remembered the thermal properties of matter in class 11, even the things will be similar. Yes, alpha is equals to delta L by L delta T. Yes, it is the change in length, it is the original length, and this is the change in the temperature. Even this is the same case. This alpha is equals to RT minus R0 divided by R0 into T. I hope those things are clear. Is it clear? Great. Now let's define the alpha temperature coefficient. How we can define it? It's a temperature coefficient of resistance that can be defined as increase in resistance per unit original resistance at 0 degree Celsius per degree rise in temperature. Yes, so alpha can be written as RT minus R0 divided by R0 into T. It's a SI unit. Look at this, it's a resistance, so this is ohm, it's a ohm into Kelvin. Yes, so this ohm has been cancelled, and the SI unit of alpha can be written as centigrade inverse or Kelvin inverse. Also resistance at particular temperature can be written as RT is equals to R0 into bracket 1 plus alpha T, where RT is the resistance at T degree Celsius. R0, it is the resistance at 0 degree Celsius, and T is the temperature difference. I hope those things are clear. Is it clear? Is it? Great. One more thing, and very important. as I know that alpha is equals to RT minus R naught divided by R naught into T. So I can write like this, it's a delta R by R into delta T. If this changes are very small, what I can have is that alpha is equals to 1 by R multiplied by dr by dt. Yes, so even alpha can be calculated using 1 by R multiplied by differentiation. It's a differentiation of resistance with respect to temperature. So if I differentiate the resistance with respect to temperature, and if I multiply this with 1 by R, then even I can calculate the alpha. A very good and logical kind of questions has been formed from here. So please do remember this. This is alpha is equals to 1 by R. Alpha is equals to 1 by R into bracket dr by dt. Yes, purposefully write the capital T so that you will know always that this is for temperature and not for the time. I hope these things are clear. Is it clear? Let's look at the questions. Let's say the resistance of a wire is given as R is equals to R naught plus alpha T plus beta into T square. Find out temperature coefficient for the given wire. So how could I calculate this? I have been given the value of a resistance with respect to temperature, and as I can see that as temperature changes, my resistance will be changes, and I need to find out the temperature coefficient. That means I am requiring alpha. So for alpha I can write like this, it's alpha is equals to 1 by R multiplied by dr by dt. Let's just calculate dr by dt on our first step. It's a dr by dt that should be is equals to d by dt of R, and R can be written as R naught plus alpha T plus beta into T square. So d by dt of R naught, it is a constant term which will be in 0, plus alpha plus beta T square, it's a 2 beta T. This is the value of just dr by dt. Now alpha, it's 1 by R multiplied by dr by dt. So that can be written as dr by dt, it's an alpha plus 2 beta T divide by it is R naught plus alpha T plus beta T square. This should be the value of alpha. I hope these things are clear. Is it clear? So can you do this kind of questions? Great. Now next level of question. The question says that let's suppose a resistance of platinum wire at 0 degree Celsius, at 100 degree Celsius, and at certain T degree Celsius has been given. At 0 degree Celsius it is a 5 ohm, at 100 degree Celsius it is a 5.5 ohm, and at T degree Celsius it is 5.2 ohm respectively. I need to find out I need to find out that find temperature where resistance is 5.2 ohm. This is your requirement. So look at this very carefully. Observe this relation. What they have provided the temperature, they have provided the different temperature and respective resistance at that particular temperature. At 0 degrees Celsius it is a 5 ohm, at 100 degrees Celsius it is 5.5, and at T degrees Celsius it is 5.2 ohm. So my basic relations is that RT is equals to R naught into bracket 1 plus alpha into T. This T represents the change in the temperature. So if I write like this, it's an, let's suppose that R of T is equals to R naught into bracket 1 plus alpha. Let's suppose this temperature difference can be written as T minus of T naught. Now, what is resistance at 100 degrees Celsius? R100, which should be resistance at 0 degrees Celsius into bracket 1 plus alpha into 100 minus of 0 degrees Celsius. And what is resistance at T degrees Celsius? It is R naught into bracket 1 plus alpha into T minus of 0 degrees Celsius. So this is relation number 1, this is relation number 2. If I take a ratio of these two relations, this 2 has been gone. Now what I can have, I am having that R at 100 degrees Celsius, which is a 5.5 ohm, R at T degrees Celsius, which is a 5.2 ohm. That would be equals to 1 plus alpha into 100 divided by 1 plus alpha into T. Yes, is it clear? So what can I do? If I solve this, what I can have a value of a temperature T, and that T could be written and T could be find it out at 40 degrees Celsius by solving this. I hope these things are clear. Is it clear? Even you can use one of the shortest formula for this. So let's just write it down, and if you wish you can remember this, that at any temperature T would be RT minus of R naught divided by R of 100 minus of R naught multiplied by 100 degrees Celsius. You might have used this relation, while you were studying the thermal properties of matter. Even you can go with this. There is no problem in this. Only the calculation would be a lengthier, because here you require two unknowns. One would be alpha, another would be a T. So here you need to solve for the alpha as well, and then you can find out the answer, which is a T is equals to 40 degrees Celsius. While in this case, no need to find out an alpha. We are just eliminating alpha, and then the relation has been formed. So if you wish, you can remember this. I hope these things are clear. Is it clear? So can you do this kind of questions? Is it possible? Can you? Are you sure? Okay, great. Now let's look at the dependency of a temperature on resistivity. Now we are talking about the resistivity. So let's first begin with the metals. We say that the resistivity of metal conductors increases with temperature, and such materials have positive temperature coefficient. This is required. This is very, very important term. It's a positive temperature coefficient. Now what I mean when I use a positive temperature coefficient, so if due to increase in temperature resistance of a material increases, That means temperature coefficient. That means temperature coefficient is positive. I hope these things are clear. Yes, if temperature increases and even resistance increases, my alpha is positive. If reverse is the case, let's suppose there is a increase in the temperature, but there is a decrease in the resistance. Then we can say that it is having a negative temperature coefficient, such as the case with the coppers is there, aluminum is there, and so on. So let's have a graph. That this is the graph for the resistivity versus the temperature. If you observe this carefully, that we can divide this into two sections. At lower temperature, near to the 0 degree Celsius, it is non-linear, and as soon as the temperature increases, it is somehow linear at the higher temperature. But even if you don't remember linear, non-linear, don't worry. But you need to just remember that as temperature increases, my resistivity is increasing. Let's have a look. Yes, this is the case. So as soon as temperature increases, for metals, I repeat, for metals, my resistivity always increases. Yes, and as resistivity increases, my current will be decreases. So you must remember all these things, that if my temperature increases, my resistivity increases. I'm talking about the metals. And as my resistivity or my resistance is increasing, my current is decreasing. Yes. Now let's have a look. What is the situation with the semiconductors? For semiconductors, resistance decreases with the temperature. That means if temperature increases, look at this, resistivity is decreasing. That means if temperature increases, resistivity decreases, conductivity increases. I hope these things are clear. That's why we are using semiconductors at every possible places, because this material have a negative temperature coefficient. This material is having a negative temperature coefficient, because as soon as temperature increases, its resistivity decreases. Yes, so this is the case with semiconductors. Now let's look some alloys. Certain alloys like nichrome is there or manganese is there. This all have a large resistivity but very small temperature coefficient of resistance. For this reasons, alloy like manganese are used in the production of high precision resistors. These are the resistance which can give a very accurate value. Even a very small tolerance would be there. And because we require a certain kind of resistance at certain plants, such as the power plants or the nuclear power plants, or when we say that we are going to manufacturing something for our militaries. Yes, at that point of time, precision and accuracy is essential and very essential. You cannot have any kind of tolerance with it. So at that point of time, manganese are used to produce a high precision resistor. This is the resistivity versus temperature graph for manganese. As you can see that there is a very big difference in the temperature. It's a 0 degree Celsius, but there is a very little difference in the resistivity at 0 degree Celsius and resistivity at T degree Celsius. I hope these things are clear. Is it clear? Let's look at the knowledge plus. Now let's suppose that I have plot a certain graph for the I versus V, and as you can see that there are two straight lines, and when straight lines, that means they have been given for the ohmic conductors. So for a given ohmic conductors, the current versus voltage graph at two different temperatures T1 and T2 has been formed. Now from the graph I need to find out that which temperature is higher or which resistance is higher and all that stuff. How could you do this? Take a time of 10 seconds and let me know. How can we do this? Let's suppose that I want to find out that T1 is higher or T2. How could I do this? How could I? What I know is that my graph is for the I versus V. So if I take a slope of this, it's a delta Y by delta X. On my Y axis it's in current, and on my X axis it's in voltage. So my slope will give me a 1 by R. It's a 1 by resistance of that material. This is the slope. So if I observe this, what I can have is that the resistance of this wire is greater than the resistance of the first wire. So value of resistance 2 is greater than the value of resistance 1. And as I know that this are the metallic conductors, their resistance will increases. As the temperature increases. So I can write it's a T2 greater than T1. I hope these things are clear. Is it clear? Any doubts? No? Okay. Shall we go for one more? Same pattern. Suppose in the previous question, graph was given like this. It's a voltage versus current, and two straight lines were there. Let's suppose this is for temperature 1, this is for temperature 2, and they have asked me that find out temperature of which wires is higher. Let's suppose this is wire 1, this is wire 2, and I need to find out that which of the following wire having a higher temperature. So let's do the same thing. Let's calculate the slope. It's a delta Y by delta X, and here it's a V by I. When I say V by I, that means I'm going to have a resistance as a slope. In the previous case it was the 1 by resistance, here it is the resistance itself. So if I observe this carefully, it's a theta 1, it's a theta 2. So if theta 2 is greater than theta 1, that's why slope is greater. And as slope is greater, which is M2 is greater than M1, that means resistance of second wire is higher as compared to the resistance of first wire. And as their resistance are higher, their temperature must be higher. It's a T2 must be greater than T1. Is it clear? Is it? So can you do this kind of questions? Will you? Great. Let's have a look certain MCQs. First, resistivity of a conductor. Resistivity of a conductor depends upon area of cross section, material, and temperature, length, all. Resistivity of a conductor never depends on the area of cross section. It never depends on the length as well. It depends on the material and temperature. You can remember this thing, that resistivity of a conductor is independent of area or length of conductor. That resistivity of a conductor is independent of the area or length of a conductor. It does not depend on the cross-sectional area or length of a conductor. So it depends on the material and it depends on the temperature. I hope these things are clear. Next question. with the increase of temperature, the specific resistance. Now, first question, what specific resistance? What does it mean? Yes, it is the resistivity. So when and when they want to ask resistivity, they can use this word. It's a specific resistance. Yes, with the increase of temperature, the specific resistance of a metal, it increases. Yes. Next question. Let's look at the next. The temperature coefficient of resistance of conductor, it is positive. If they have asked about the temperature coefficient of semiconductors is negative. So for semiconductors, temperature coefficient is negative. For temperature coefficient of resistance of conductors, it's a positive. Is it clear? Great. So now let's move to the next topic. It's a color coding of resistor. So actually what color coding is all about, when and when you go to the market and you just ask the seller that give me a resistance of, let's say, any value, 100 ohm, 200 ohm, 6 mega ohm, 10 mega ohm, and so on, what you are going to have is something like this. This is the photo of a resistance that is available in the market. This kind of resistance are known as the carbon resistors. These are the carbon resistors. But if I have been asked for the, let's say, 100 ohm, how could I identify from this that whether it is of 100 ohm or not? Because even on the resistor there has not been written anywhere that this should be the value of this resistance. So how can I come to know that what is the value of this resistance? For this, we have defined a color band system for resistance. And for what color band systems, that we have differentiate this all four bands and given them certain codes, and when I evaluate this codes and this pattern, that what first band is talking about, what second band is talking about, what about third and fourth. Yes, so when and when I came to know that what is the value of first, second, third and fourth, I can have a value of a resistance, so I can get that whether it is of 100 ohm or not. So how this can be decoded, how the color band diagram can be decoded, let's have a look. This is the color band system. As you can see that this is the first, this is the first digit, it's a first band, this one, this is the first digit of value of a resistance. This second color band, this is the second color band, it is the second digit. The third band is known as the multiplier color band, it's a multiplier. And the fourth band, it is the tolerance color band. So let's again repeat this from here to here. It's a first band, which represents first value of a resistance. If it's a second digit, it's a second value. Third, it would be a multiplier, and fourth band, it's a last band which represents the tolerance. Now what is the coding? What is the coding of each color? Let's have a table of it. Yes, you need to remember this. This is essential. Even this has been asked. So this is the color coding. Yes, let's start with the black, then brown, then red, orange, yellow, green, blue, violet, gray, white, gold, silver, and no color. For you need to remember this table as this is the color lines. Next it would be a number, next it would be a multiplier, and next at last it would be a tolerance. you must remember that your number must be starting from the zero, because what our practice is, that we start our number with 1, and that's why whole table will be incorrect one. So please do remember that our table must be started from the 0. So that is from 0 to 9. Even a multiplier, it's a 10 to the power 0 to the 10 to the power 9. And for gold and silver, I am having a 10 to the power minus 1, 10 to the power minus 2. And last, it's a tolerance, that there can be a variation in the value of a resistance. And if it's a gold band, there can be a tolerance of 5%. If it's a silver, it's a 10% variation could be there. And if it is a no color, there could be a variation of 20%. I hope those things are clear. Is it clear? Yes. Now one thing, how could you remember this? How could you remember this color diagram? So you can have this relation. It's a B.B. Roy of Great Britain has very good wife, where gold and silver. Yes, so from here you can pick one liter of each, and you might find this easy to remember. This is B, this is B, this is R, this is G, this is B, this is V, this is G, this is W, this is G, and S. Yes, one more acronym which I generally use is the B.B. Roy. It's a B.B. Roy of, or I can say B.B. Roy goes Bombay via Gateway. Yes, this B is stand for black, this B is for brown, this R is for red, this O is for orange, this Y is for yellow, this G is for green, this B it's for blue, this V is for violet, this G is for gray, and gateway it's something like this, it's a white. And then you need to write gold, silver, and no color. You can remember whichever you like. Yes, you can go with this, but the one thing is required, that you must remember this, because this can be asked. Yes, so how could I write this now? Let's have an example that first band it's of yellow, another band is of green, another band it's a third band which we call as a multiplier, it is of red, and last band it is of silver. So first band it's a first digit which is a 4, second band it's a second digit, it is a 5, third band it is a multiplier. For red if you see the color code, this is for red, it's a multiplier 10 to the power 2. So this is 4 5 multiplied by 10 to the power 2, and the last band it is of silver. And if it is of silver, that means it represents the tolerance, it's a tolerance of 10%. So this is 10%. So if I combine this, I need to write this first two digits, it's a 45, then multiply this digits with 10 to the power 2, it's a multiplier, that's why it has given a name of 10 to the power 2, and last it was the tolerance, this is ohm. So here 10% is the tolerance, means that there could be a 10% error in the value of its resistance. So if I go through this, it's a 4500 ohm, and 10% of 4500 ohm, it is a 450 ohm. So value of this resistance can go up to the 4500 plus 450, or even it can go up to 4500 minus of 450. These two are the possibilities with the resistance. I hope the things are clear. Is it clear? Is it clear? Okay, let's have a look to the certain MCQs. First, the first color band indicates, what does it indicate? It's a first digit. I hope the things are clear. The second color band, it's a second digit. Is it clear? Yes. The third color band indicates multiplier. The fourth color band, it's a tolerance. Look at this, you have solved 4 questions in less than 10 seconds. Great work. Keep going. And last, if the color code for a resistance is yellow, green, red and silver. Yes, it's a yellow, green, red and silver. The value would be, this is the first, second, third, fourth. Value of yellow, it's a 4. Value of green, it's a 5. Third band, which would be a multiplier, so it is a 45 into 10 to the power 2. And fourth band, which is showing the tolerance, it's a 45 into 10 to the power 2 plus or minus 10%. This is O. I hope those things are clear. Is it clear? So can you do this kind of questions? Yes, this is the topic which can be asked. Basically in this session we have discussed about the temperature dependency of resistance and resistivity and color coding of a resistance. So please practice this kind of question. This will help us. Thank you. Have a good day. Take care.